In this video, we look at an example of a line integral of a scalar function from section 6.16.1. In general, we're looking at the integral along a curve of some function f ds. Okay, and in this case, for this particular example, this is the notation in general. But for this specific example, we have a function that's given as f of xy is equal to x plus the square root of y. And our curve C is this curve shown here. It's the curve that starts at the point 0, 0 and moves along this arc of the parabola, starts at 0, 0 and goes along a parabola to the point 1, 1, and then we go from the point 1, 1 and we go a second step and we go back to the point 0, 0 along a line and back to 0, 0 along a line. Okay, so this curve is really made up of two pieces. So the curve C is made up of a curve 1, and the book uses a notation union curve 2. Curve 1 is the parabola section, and then the straight line section is curve 2. Okay, so the way to tackle a line integral, okay, where the curve is made up of two separate curves, okay, is to split the integral into two. Do the integral, the line integral of the function along the curve 1, and then add that to the line integral of the second curve. Okay, so we're going to split this problem into two steps. Okay, remember our function is the x plus the square root of y. We'll do this as the first integral, and then the second integral we'll do. Okay, so let's go ahead and work this problem out on the next page. Okay. So let's recall that the meaning of the line integral of some scalar function, okay, along a curve C, okay, is the integral from time t is equal to a to t equals b. Okay, you find the time, find a and b by the time needed to go between the endpoints. The endpoints of the curve. Okay, you will then have a function. You will need to parameterize that curve, so C will be given by some r of t, and since in our example the curve is in the xy plane, we'll need to find an x and a y. Okay, and then the third step will be to find the function along the curve, which means that find the function, evaluate it wherever you see the x, put a x of t, and wherever you see the y, put a y of t. So this notation, we mean the function along the curve. Okay, so f evaluated at r of t, okay, and then that gets multiplied by the magnitude of the velocity vector, okay, dt. So here's the meaning of this problem. So in this case, our first curve was the part of the parabola that went from 0, 0 to the point 1, 1, and it was given by y is equal to x squared. Okay, so we're going to look at the curve then, r of t, or r1 of t in this case, is going to be the easiest way to parameterize that parabola is t comma t squared, and therefore t has to go from 0 to 1, because x is equal to t, and when x is equal to 1 at t equals 0, x is equal to 0, and at t is equal to 1, x is equal to 1. That means that here we're at this point at the curve at t equal to 0, and we're here at time t equals 1. Okay, so there's our curve, and we have done the parameterization and found the times needed. Okay, so what we can say at this point is that the integral of this function along the first curve is going to be the integral from time t equals 0 to t equals 1. And then I need the function along the curve, and since the function was x plus the square root of y, okay, wherever you see the x, you're going to put a t, and wherever you see the y, we're going to put a t squared. Okay. And then we need the magnitude of the velocity, and then integrate with respect to t. Okay. But the curve was t comma t squared, so the velocity vector is 1 comma 2t, and the magnitude of that velocity vector is the square root of 1 plus 4t squared. Okay, so if we were going to do the integral along the first part of the curve of this function, integrating with respect to arc length, that we will get the integral from 0 to 1, okay, t plus t square root 1 plus 4t squared, integrate with respect to t. Okay, so this is the line integral along the first section of the curve. So we're integrating from 0 to 1, 2t square root of 1 plus 4t squared dt. Okay. And this integral is a pretty straightforward u substitution integral. U would be equal to 1 plus 4t squared. Du would be 8t. So du divided by 4 is equal to 2t dt. Okay. So this integral is actually the integral sorry, how to write this, square root of u over 4 du, and then you integrate from u is equal to, when t is equal to 0, okay, u would be equal to 1, and when t is equal to 1, u will be equal to 5. Okay, so that's a pretty straightforward integral. Let me write this down so before I move to the next page. U equal 1 to u equal 5. So it's a pretty straightforward integral. Okay, let's work it out on the next page, add page below. Okay. So the integral along that first curve, f ds, turned out to be the integral from u is equal to 1 to u is equal to 5. U is equal to 5, square root of u over 4 du. Okay. Square root of u is the same thing as u to the 1/2. Therefore, when you integrate it with respect to u, you will get u to the 3/2 divided by 2/3. So we'll get 2/3 times 1/4 u to the 3/2 power, evaluating from u is equal to 1 to u is equal to 5. Okay, which will give you 1/6 u to the 3/2 from 5 to 1. So you get 1/6 5 to the 3/2 power minus 1 to the 3/2 power. Okay, and that comes out to be some number. I will let you figure that out as a decimal. Okay, the next part of the problem, this was only part. Remember that we were computing the integral, the line integral of the curve of f ds, and curve C was made up of two curves. Okay, and so we've done the first part. That is the number we just found. Okay. Now we need to add that to the second part. And the second part of the curve was integrating along the line from 1, 1 to 0, 0. And we had to go in the direction that they told us. We needed to integrate it from 0, 0, 0 to 1, 1 along a parabola. And now we need to work our way from along the line from 1, 1 back to 0, 0. So we need to find this line, and that line starts at the point P being 1, 1 and goes back to the point Q being 0, 0. So the vector from P to Q is Q minus P, which is negative 1, negative 1. And then the line goes through the point, let's see, P plus PQ times T. That's the equation of a line. The point P is equal to 1, 1. The direction vector of negative 1 times T. And therefore, our curve, in this case, is a line, 1 minus T, 1 minus T. And then the times we're integrating along are from times 0 to 1, because if you look at the second curve evaluated at time 0, you're at the point 1, 1, and then 1 second later, you're at the point 0, 0. So this is the curve that we need to integrate along. So how do we do that part? The integral along the second part of the curve of f ds is equal to the integral from time t equals 0 to t equals 1. I need the function along the curve. In this case, the function along the curve is x, which is 1 minus t, plus the square root of y. Y is also equal to 1 minus t. And then I need to integrate with respect to, times the magnitude of the velocity dt. Okay. Well, the velocity in this case is equal to negative 1, negative 1, the derivative. The magnitude of the velocity is the square root of 2. Okay. So the integral that's in our future is the integral from t equals 0 to t is equal to 1 of 1 minus t plus the square root of 1 minus t times the square root of 2 dt. Okay. And that's the integral that we need to spend some time thinking about. I'm going to jot it down on my scrap piece of paper here before I move to the next page. Okay. So we need a little bit more room to work, so let's add a page below. And then we have the integral along the second part of the curve, f ds, okay, is equal to the integral from time t equals 0 to t is equal to 1. We can split that integral we had into two pieces, square root of 1 minus t dt plus the integral from time t equals 0 to t equals 1, square root of 2 times the square root of 1 minus t dt. Okay. This integral, pretty easy. The antiderivative of square root of 2, 1 minus t is just t minus t squared over 2 with the square root in front of that, and evaluating from 0 to 1, which is easy. We'll call that a number. Okay. Second integral plus the square root of 2 integral from 0 in time t equals 0 to t equals 1, square root of 1 minus t dt. Again, this is a u substitution integral. Let u equals 1 minus t. Du is equal to negative 1 dt. Okay. So when you switch and change the variables, you get square root of 2 integral of negative square root of u du, and then at time t equals 0, u is equal to 1, and at time 1, u is equal to 0. Okay, which again is a pretty straightforward integral, negative square root of 2 u to the 3 halves with a times 2/3 on it. And then you evaluate that from u is equal to 1 to u is equal to 0. Okay, which will give you, when you plug in negative square root of 2 over 3, okay, just get all the constants combined, plug in 0, 0 to the 3 halves minus 1 to the 3 halves, which is equal to 2 square root of 2 over 3. So the integral along that second curve of f ds is just equal to whatever number you got from above plus 2 square root of 2 over 3. And therefore, in conclusion, the integral along the curve of f ds is the number that you got from the first curve plus this number plus 2 square root of 2 over 3 from the second curve. And that would be your answer in a completed solution to the line integral of this function, x plus the square root of y, along the curve that's been shown here in the graph, where you integrate along the parabola to 1, 1, and then you come backwards along this curve in positive time back to the point 0, 0. And the answer is going to be some number that you got from these numbers. Okay? So ends this video.